research. So I think it's really a pleasure to hear from them.
So when should I start?
Okay, just a brief announcement. We started the live YouTube streaming of this session in the Italian Society of Chaos and Complexity YouTube channel. Okay, just this brief announcement. So sorry, Ron, the floor is yours. Ron, can you hear us?
So I can start?
Yeah, the floor is yours. Thank you.
Okay, thank you, Chairman. Thank all of you for coming. I'm so glad to have a chance to come here to meet many old friends. I have many Italian good friends, and today I'm so excited to have a chance to come here. Now, okay, so can you see my PowerPoint? Can you hear me clearly? Give me a response. I want to make sure everything okay, and then I start it. Can I hear you?
Ron, at least
Yes, Ron.
I hear you very well.
Yeah. Everything is
very, okay. Very good. Okay, I prepare my talk for maybe 35 minutes, something like that. The topic is about synchronization that you are familiar with. I talk about so-called optimal. I will let you know in what sense is optimal. Of course, optimality can be defined in many different senses, right? In many different ways. So I'm going to talk about our topic, but by the end, I will show you what we are doing now, what we get recently on this topic. Synchronization is a beautiful topic. So this is a synchronizing swimming. So I will get back to this picture later on. From the picture, you can see that it's a symmetrical, it's a homogeneous, right? That's what I need. Now, just to start, because a couple of young students maybe not exactly working on synchronization, so give you some background, just 1 minute or two. Synchronization is very useful, in particular in our engineering and technology areas. Because all the words, keywords, or book titles are here, I don't have to explain to you in details. So this is one example. Now here's another example, although a few years back, but still going on. Synchronization in not only in our electronic engineering, but also in biological sciences, in some way, in some form, is useful. So that motivates us to study synchronization of complex networks. Now here's the agenda. I will talk about synchronization and criteria, and then I will define what we call this optimal about synchronizability. By the end, I will show you. Recently, we look into higher order topology of networks. I know Stefano is going to talk about high order also, so we have a little overlap. So I will prepare for you. We look at a network. So first of all, we have a general formula or equation. We have a network of capital N nodes. So the number I node usually is nonlinear. And then node number J connect to number I through this linear coupling. If J indeed connect to I, and then this Aij is 1. If not connected, then this Aij is 0. So you put the Aij together, you get the adjacency matrix. C is coupling strength. Today, we will use it. So in the simplest case, all coupling strengths are the same. And then I can put out without index. I think more or less that's it. But we are going to look at the Laplacian matrix because we are going to use eigenvalue. So if you put the adjacency matrix down here, and then you use the discrete matrix to subtract it, you get the Laplacian matrix. The nice thing is that you get all non-negative eigenvalues. So if the network is connected, you have only one single 0 eigenvalue. Starting from lambda 2, all these are positive. And this is what we call spectral gap in mathematics or algebraic connectivity in network science. So I will look into this eigenvalue lambda 2 in particular today. And also I look at the maximum one, lambda n. That is the formulation or the basic setting. So now we have a network. So I copy the network here, and then we are going to talk about complete state synchronization. It's defined this way. Graphically, it looks like this. Because even synchronization, there are many different forms, right? So we look at this basic one, the simplest one. The definitions are here. Now, I think you all know about this. And then when we look back, we have been working on network synchronization for 20 some years. The first criterion that Professor Xiao Fang Wang, now in Shanghai, and me developed. So at that time, he came to Hong Kong to visit me. Then we thought about this. So we come up with the first criterion. We look at the lambda 2. So I will show you on the next couple of slides. But here, just show you that lambda 2 is the key parameter, the eigenvalue of the Laplacian matrix. And this lambda 2 would be positive. That's why I use Laplacian rather than adjacency matrix. Okay, I look at the chat room. Then the same year, slightly later, Pecora and his postdoc, they develop another criterion. These two criterions are consistent. So they said that also why not take into account lambda n? So they look at the ratio. And then today I will talk about these two, but because these two are consistent, so let me just talk about one. And then let me just talk about this ratio, because it's popular. Everybody use this, although we developed the criteria a little bit earlier independently, but that doesn't matter because the same thing in some sense. In more general situation, actually, the synchronization area, the location of eigenvalues, for example, for this ratio, can have different intervals. So this is too complicated, and I will not talk about this today. And this is not that important. So most importantly, we are going to look into the ratio as a criterion. Now, somehow the computer reacts slowly. Okay, now just to give you, in particular, some young students, give you some idea how we derive this criteria. Okay, you have a network, right? So if you put everything together, you step it up into a very high dimensional. You can put it in the very compact network form using Kronecker simple. And then you don't worry about the minor details. Because I'm going to use eigenvalue, then I need to use the matrix. So we do linearization. You linearize it, you get a Jacobian matrix here. This could be a nonlinear function. You linearize it, you get another Jacobian. And then you have a linear, very high dimensional system of equations. Then you look at this and then you look into the eigenvalue. Where's the eigenvalue now? It's in the matrix A here. All the others, after you plug in the equilibrium point, they are constant matrices. So the eigenvalue will come from here. And the coupling strengths also affect the eigenvalues. Now, there are some simple assumption. For example, the function is Lipschitz. So after you think linearization is bounded from above, or simply you just say that this Jacobian is uniformly bounded from above. And then if this term, now I'm talking about only the idea. If this term is bounded, you see that if you make this term as big as possible or as selective as possible, and then the second term will dominate the first term. So you say, I don't look at the first term, I look at the second term. And the second term, what is important is the eigenvalue. So later on, we look at the linear term with a matrix here. Finally, we look at the eigenvalue. That's the idea. Okay, that's a whole process. Now, after you, I copied it here, and then after you linearize it, and then you can look at the boundary. That's an idea from Picora and Carroll. So they look at this issue actually much earlier than we did, and then they said that now again just an idea. If you don't care about those minor details, because within 30 minutes or so we cannot get into all minor details. Now the idea is that if you look at that, then you see that I look at the boundary to be conservative. So I look at the eigenvalue between C times A. Let me call this alpha. I look at the boundary, the lower boundary. And then I can draw a curve. Of course, technically, you look into the so-called conditional Leopold exponent, but if you don't care about the detail, the idea is that now I found a boundary. Inside the boundary, all eigenvalues are located. So if the boundary is over there, then you don't have a negative part, then synchronization is not possible. Now, if the eigenvalue, if the boundary come down here, you see that over here, the Leopold exponent is negative. And that more or less, you can think that all the eigenvalues, they are negative. They are, if there's a complex and then the real part is negative, then you know the system is going to be stable. Now, if this system is stable, you look at two, you do subtraction, you get the error. And actually, this is the same form. You get the error dynamic system. So if an area dynamic system is stable, and then the error goes to 0, and that means that the two state variables or vectors, they synchronize, right, according to the definition. So that's the whole idea. Now, technically, the boundary is good for us to use. So Stefano Wang and I developed criteria, and we look at that lambda 2. If lambda 2 is over here, so all the other lambdas is bigger than lambda 2, then certainly all eigenvalues are on this side. And then you guarantee the whole network synchronized. And then the ratio is in this situation, because this is a kind of like the eigenlocus. It's a polynomial of a higher degree. It can come down and go out again. And in that case, the ratio should be located of here. It will appear here. And then if a ratio is over here, you know this above exponent will be negative. So the error system will be stable, converge to 0. Then the original network will synchronize. So that the two criterions take care of two situations. There's no conflict. But if a situation is like that, then lambda 2 can be as big as possible. If the curve looks like that, then the ratio should be somehow in the middle, would be more robust because a little perturbation would not drive the ratio out from this region. It will not fall to the left or right. So in this case, you want the ratio to be somehow in the middle. And you know the ratio, right, cannot be bigger than 1. So the maximum will be just 1. So we want the ratio to be as close to 1 as possible. In other words, as big as possible in that sense. And here, the lambda 2, you want it to be as big as possible to the right-hand side. And then the situation will be more robust. A little perturbation would not push the lambda 2 to be the left-hand side to be out of this region. Now, this is from that robustness point of view to look at this. And if you look at the performance of the synchronization, the bigger lambda 2, it converges the faster. And here, the bigger the ratio, it converges the faster. So in all this sense, we want to have a result that in this situation, we want lambda 2 as big as possible. In this situation, we also want to have the ratio as big as possible. So I summarize it here, that the same picture. So I want to put it together. You have the whole idea. And then the criteria now to summarize it is that if I only have lambda 2 to look at, or in this situation, I hope the lambda 2 as big as possible. If I have a lambda n as well, and then I hope that the ratio as big as possible. And certainly the ratio cannot be bigger than 1. So as close to 1 as possible. And in this sense, we can talk about so-called optimality. So as big as possible. In that sense, if it's big, then it's better. So in that sense, we are talking about optimal synchronizability. Okay. So again, optimality can be defined for many different things. So here we define it for this situation. Now, with this, then we try to find that. Now the idea becomes clear. We want the eigen value to be like that. So we want to find out what kind of network can give you this kind of eigenvalue or ratio, right? Eigen ratio. And then we start with a simple example to have some idea. Now let's say we have a Laplacian matrix like that. I allow you to move around the connection. For example, here you have a connection, now you can move it to here. For the time being, let's say you don't add any addition connection, you don't subtract any, remove any connection, but you can move the connection around. So how should you move the connection such that you have the largest possible lambda 2, you have the largest possible ratio. And then for example, of course, we can use computer to try all possibilities, right? Combinatorial for small size is fine. Computer run it and give you a solution. Oh, this is the best. Now the best turns out it looks like this. So it's symmetrical, it's homogeneous. And when you look at the matrix, you'll see that it's uniformly distributed. In that case, the ratio is maximum. If you move one to somewhere, you destroy the symmetry, this becomes smaller. And then you can find many examples like this. So the observation is that, the optimal structure of network that give you the maximum value of the eigenratio should be homogeneous and also symmetrical. And then, of course, when you do research, you start with some examples, you get some idea. Then now you want to have a general theory or a general method, right? You have a general algorithm, and then we cannot find it. So we try to do it numerically first. And so you can formulate a numerical optimization problem easily. You maximize the ratio, subject to some constraint. The constraint guarantee that you keep all the degrees constant, unchanged. You make sure that when you move along these connections, the network made to be connected. You don't separate into pieces, right? So you have some constraint, and then you run numerically. You can find an optimum solution for different sizes, and that's what we did. Now, of course, several years ago, and then from there we try to find some common properties and to help us to develop some general theory. That's the procedure of the research. And then what we found out is that, okay, now we have like hundreds of examples for lower dimensional cases. And then we observe that the optimal solutions are all homogeneous, all symmetrical. And then I said, okay, graph theory provides some tools to use. Now let's consider only a subset of networks. Those networks are homogeneous and also symmetrical. And then how do you guarantee or describe this kind of network? And so from graph theory, we get some idea. We said, okay, first we can require all degrees are the same. So in graph theory, this is called regular network, right, of degree R. So the degree can be higher or lower. This doesn't matter depending on the size of the network. But we want all nodes have the same degree. And then we look at the so-called path sum. The path sum is, I show you the picture because it's not very commonly used. Now, for example, I'm node number 1, I have a distance to 4, which is 1. My distance to 5 is 2. My distance to 9 is 4, right? So I add all these paths together. That's my path sum. You can do that also. He can do that also. So now we require that we expect to have a network that give you all these path sums are equal. And then we look at one more, the girth. Girth in graph theory is defined to be the shortest cycle length. For example, for node number 1, there's a cycle triangle, the girth is 3. There's another triangle, there's also 3. But for node number 4, right? Look, it has a 3 triangle here. It has a bigger one over there, connect to number 4. So for number 4, the girth is 3. We look at the smallest, the shortest path sum in the loop. We don't look at the larger one. So that's the definition. Okay. With this definition, now everybody has a certain number, right? Some may have 0. Now, like this one, it has 0. So this is not a good picture to use. I mean, later on for our purpose. But girth can be defined. Then we want everybody has the same girth. Now that looks like everybody equal, right? So that network you can picture at the moment that later on when you look at the picture, everybody is the same degree, the same distance, the same cycle length, things like that. Indeed, that gives you the best network structure with the largest eigenratio. For example, if you have 4 nodes, you have this structure. 6 nodes, you have this structure. Now, if you change the structure a little bit, let's say you change this connection to this connection, I guarantee that your ratio will be smaller than my ratio. So this gives you the largest eigenratio. That means the best synchronizability in the sense I just defined. So when you increase the number, all these solutions, optimal solutions, you can go even further. We can go to more than 100. I just show you a few. Now, this is what we have done a few years back. We have an idea from observation, from simulation, from this simple analysis that the best network topology, which give you the largest possible eigenratio, should be symmetrical, should be homogeneous. And then in graph theory, you have some knowledge. You say, oh, maybe there are more tools to use. That is a higher order topology that may give you more information about that. Now, what is a higher order topology? Let me introduce some basic one for you. First of all, some notation. M0 is a number of nodes. M1 is a number of edges. Now you see that you go from one node to 2 nodes to 3 nodes to 4 nodes and so on. So a number of triangles, a number of tetrahedrons. So you just go more and more nodes, and then you can define the number of those those basic. You can call them motif, but this is a special motif. So you can have all these numbers for a given graph, right? And then Euler define that if you put this number there automatically plus minus, you get a number. And this number is a characteristic number. It's a kind of invariant number in some sense. So this is a very useful number called Euler characteristic number. All right. So now I define this. I will use it today. The second higher order topology concept that I need to use. We start with adjacency matrix that you know. We define so-called boundary matrix. Now, adjacency matrix is from node to node, right? If I connect to you, you connect to me. You know, you have this 1 and 0. So this is between node and node, the standard adjacency matrix. Actually, this is called boundary matrix already. But the next one from node, between node and edge. So you go like one level higher, and then you have this matrix. In matrix theory, in graph theory, we call this instance matrix, right? Special name. But now today we call this a boundary matrix. It's between nodes and the edges. Now for this, you can calculate the rank. And here, of course, you need to use a binary operation, not the general operation, binary. You can calculate the rank, and this is what I need to use later on. When you have a matrix, of course, you can calculate the rank, right? So the linearly independent market right here, but just keep in mind that I can define a rank. I will use the rank. Now, from node to node, and now from node to edge, I can go up. I can go up from edge to face, right? From edge to triangle, and then I can calculate the rank. And then I can go even higher, face to face to hydrogen. I mean, when you go up, I don't remember the name, when you have a 5 or 6 or 7, there's some English names that are not very popular. Okay, yeah, you can go up, just hydrogen, and then you can just go up. So what I need to use is this rank of the so-called boundary matrices. Now with this, and then Betti, so again, Italian mathematician, long time ago, he defined so-called Betti number. Now this Betti number is used, you know, the number, the Euler number used, remember the M earlier, and then you use the rank. You put it there, and then you can calculate the Betti number, beta 0, beta 1, beta 2, and so on. It has certain meanings of a higher topology. Now, cavity is a generalization or extension to a higher level of the cycles. So you can go up and up to higher and higher order. When you have a very large size, very complex network, and you can go very high. And then Euler, Poincaré together, they have a formula. They identify that, oh, these two numbers are actually they equal. So here's the Euler characteristic number, and here the beta is Petit number. So they have this relationship, really nice. Now, today I will show you that they are useful. So we found out that just a couple of years ago, we found out that we can compare the synchronizability by looking at their structure and then calculate their Euler characteristic number, the Petit number, and use that to make a decision. Namely, you have some new criterion that use a higher order topology. And it turns out to be even better. Now, to show you one example, let me compare these four types of networks you're familiar with. A regular network like a ring, then small world network, you mix up a little bit. Then random network, you mix up a lot. Then the network that I just showed you, the same degree, the same curves, the same path sum, we have a special name for it, just for convenience. We call that totally homogeneous network. So let me compare these four different but typical type of networks. And here's the result. And then we work out, of course, a small size, a little bit bigger sizes. We work out many. And here I show you one particular case, just 20 nodes only. So you look at the regular networks, small world, random, totally homogeneous. And then you can calculate how many triangles that you have inside there. So that's the girth, right? The smallest cycle. And then you can calculate the Euler characteristic number. You can calculate the Petit number. Meanwhile, you calculate lambda2 and the ratio also to compare. Right, so you for this four type of network, you calculate lambda2, and then you calculate the ratio, and then it turns out that the characteristic number here, the Euler characteristic number, give you a very precise criterion. The smaller the better. Because from earlier, you'll know that if you look at the lambda2, the bigger the better. So homogeneous network is better than random network. Random network is better than small world network. Small world network is better than the ring. So we already know this 20 years ago, right? And now when you compare, you see the Euler characteristic number give you exactly the same thing, but just a minus sign because of definition. So the absolute value, the bigger, the better. If you look at minus side, then the smaller, the better. So it's consistent. So I put it here. Totally homogeneous network has a better synchronizability than random, better than small world, better than the ring. So regular here, basically I mean the ring, because otherwise it's not comparable. And I think more or less that's what we have done recently. We are still working on it. And then the conclusion is the following. Now, if you allow me to construct a network, you give me a number of nodes, you give me a certain number of edges, and ask me to put them in some way to form a network such that the network has a good synchronizability as good as possible. And then I will suggest you to construct a totally homogeneous network. Try to make it homogeneous. Everybody has the same or about the same. If we cannot do it exactly the same, about the same degree, about the same curves, you know, the more identical, the better. That's what we found out. And then in terms of criteria, I show you Euler characteristic. We found out that there's a very reliable index to use. For small size, for high order, not so high order. So when we calculate the eigen, calculate the characteristic number, I show you, right? If our network is not too big, we go up to M3, M4, and then finish no more. And then we verify many of this because the computer is very fast today. And so our students have fun. So they calculate a lot. And then we found out it's always true. What I show you always true for small sizes. But we don't have a theory. We cannot prove this is absolutely correct. So it remains to be a challenge. Is this always true? Can we prove it mathematically? Okay, we don't know yet. And here also, actually, I already thought about this. So I think my time is about right. And then in summary, you see this picture really not just good looking, but actually it tells you that a good network with optimal synchronizability should be homogeneous, should be symmetrical. Thank you.
Thank you, Ron. Thank you for thank you for this very fascinating talk. We really appreciated it. Okay, so thank you also for staying in time. So it's perfect. So we have time for 1 or 2 questions, specifically for the talk of Chen or Ron, and then we will move to the second part of our event. So anyone? So if someone wants to ask a question, just inform us and we will open the microphone.
Okay, hello. Arturo gave me open my microphone.
Hi, Fabio.
I'm Fabio D'Ercole. Hi, Ron. Nice to hear.
First of all, thank you for helping IGBC. There are many friends here helping IGBC.
It was a pleasure, and I would be ready to get in again if you like. I have a question about the higher order topologies.
Okay.
I noted a little difference between the node, that is the adjacency matrix that you showed us, because then 2 nodes, you have an element 1, if 2 nodes are connected by an edge. So you use an edge to say whether you have 1 or 0 between 2 nodes. When you go to higher order topologies, for example, an edge to triangle connection, it seems to me that you put a 1 in the matrix if the edge is part of the triangle.
Oh, yes.
So essentially, you don't need an extra element. You have an edge, you have a triangle, and you say they are connected. You have 1 if 1 is part of the other. While I note a difference in the node-node connection, because then you cannot say whether a node is part of a node. You need an extra element that is the edge connecting them. So maybe I would like you to comment on this sort of difference or asymmetry between node-node and higher order topologies. Thank you.
The definition of the boundary matrix is correct. What you said is correct. If edge is inside a triangle, it's one side of a triangle, and then in the matrix you have a 1 there. If it's not in that triangle, it's not one side of the triangle, and you get a 0 there. So the boundary matrix, when you go higher and higher order, the size becomes smaller and smaller. Finally, you have no more, and then you stop. The reason this will contribute to synchronizability is that when you go to higher order, it involves more nodes, it involves more edges. I think that's the nature, that's the essence why it becomes more important. But how this relationship can be found out precisely, how can we use that to see how they affect the eigenvalues? these are really not clear yet. So people still look into the higher, let's say, second order of Laplacian matrix to look at the eigenvalue, to see how much that contribute to the lower order situation. So in other words, everything is can be defined very well mathematically, but the relationship and their role to play, if you're concerned about synchronizability, I'm not so clear yet today. So something we still need to learn, still need to find out.
Yeah. So there is space for research.
You're welcome. Yeah, the feeling is that because they involve more elements in the network, so they should contribute more.
Right. Thank
Okay.
you.
We have another question from the online audience, and then I will stop the question for Ron and move to the second talk. Please.
So I look at the chat room. There's no
They are
question.
contacting in private to Arturo. So we are supposed. So Vahid, could you open the micro, Vahid? You should be enabled to do.
You want me to open the PowerPoint again?
No, Ron, we are fine with
the chat
you.
room.
We are fine. We received a request by Vahid. So Vahid, could you open the micro if you want to ask the question?
I saw you talk to me.
No, sorry, Ron.
Cannot hear.
No, the same to me. We cannot hear. Okay, so since time is going on, I would postpone this question as well as the other to the second part of our event and leave the floor to Stefano for his talk.
Okay, thank you all.
Thank you, Ron.
Thank you to the organizers for having put together this fantastic event. I know how much effort Mattia and Arturo and all the friends of Catania did in preparing such event, and it's a great pleasure and great honor to speak together with Guanrong. Guanrong is not only a great scientist, is a real gentleman in our community. So it's really a pleasure for me to share with him these lectures. So now I'm sharing my screen, and I like to discuss with you our latest results about processes and dynamics in networks beyond pairwise interactions. As you see, this is a sort of summary of several results which we published recently. And we have a rather large group of collaborators, including, of course, Mattia Frasca from Catania. So already Guanrong introduced a little bit the need of overcoming the limit of pairwise interactions. I would like to comment a little bit on this. And I would like actually to show that considering higher order interactions in a network and actually having a completely different way of thinking about a network, it's necessary because these higher order interactions are producing network functioning which are completely different and actually are proper of such interaction. What I mean is that by means of this higher order interaction, you can describe collective behavior which are impossible in the absence of such higher order interactions. So since we are in Italy, let me start, however, with telling you that the first paper ever discussing spreading processes in a network was published on June 15, 1827, and it's the chapter 11 of the Promessi Sposi by Alessandro Manzoni, where there you have all concepts or how a secret passes from a man to another up to reaching the ear of a given person. In that case, it's Don Rodrigo. But I really invite you to have a lecture of such the beginning of chapter 11, because there you have the concept of a network, of cycles, of hubs, of ranking between different persons, the need of usage. So there are a lot of concepts which of course are written there ironically, but you see that we will use later on. Now, going for, so to say, more scientific basis, you know that in physics you have two kinds of systems, we can say. One are the continuous systems, those which are described by, sorry, one moment. Chiara, non posso, sono in una conferenza, ciao. So those were described by partial differential equations, okay? So think about fluids, think about solids, you know, that you can really describe the behavior and the evolution of such things by means of partial differential equation. And as opposed to this continuous system, you have instead distributed systems, those whose collective functioning is the results of the interactions indeed among the fundamental elements which are forming those systems. So you see, systems are formed by hundreds, millions of unitary components. These unitary components are interacting, and as a result of this interaction, you get a collective function. These kind of systems in the last 2 decades, but in fact, in many more years in the past, were modeled like networks, like graph. And the word complex network stands for the fact that we consider these units to interact with a complex, so to say, wiring of connections, with a complicated topology. However, it's clear since the very beginning that when you do this representation of a distributed system, you are doing a strong assumption. And the strong assumption you're doing is that each element is interacting with the rest of the system by, so to say, in a form which is always factorizable in the sum of pairwise interactions. Because what you consider is the sum of links. So a link is a pairwise interaction, it's interaction between two elements. Now, this assumption, we can say that is always valid when the kind of interactions you're considering are linear. Because if you have linear interaction, you can always split your complicated topology into the sum of. But as soon as your interaction is of nonlinear, that is, for example, quadratic, cubic, whatever you want, this is a very strong assumption, which not always is true. Actually, is false in many conditions. So we want, therefore, to change our perspectives and see a distributed system not like a network, but like an hypergraph, the most general way, in which you have this collection of nodes, and then you have pairwise interaction, which are links. Then you have 3-body interactions, 4-body interaction, 5-body interaction, many body interaction, so to say group interactions. And these group interactions are represented by hyperlinks, that is, links which are grouping 3, 4, 5, 6, 7 nodes. And therefore, what you have to have in mind is not anymore a network, but this collection of nodes with this collection of hyperlinks, each one having a different length, that is, one representing 3-body interaction, the other one representing 4-body interaction, and so on. Now, in the rest of my talk, I want to show you which are the consequences of doing such step. That is, representing a system not anymore like a graph, but like an hypergraph. I have no time to describe everything, so I will concentrate on synchronization because Guanrong already made a vast presentation of the issue. So here there are examples of these 3-body interaction or 4-body interactions. For example, in co-authorship network, usually the nodes are authors and the links are papers. But the situation is very different if scientists I and J publish a paper without K, then scientists J and K published a paper without I. And a third paper is published by K and I with no J. This is the closure of a triangle, is the sum, is factorizable in the sum of 3 links. Another thing is the 3 authors, I, J, and K, together, they wrote a paper. So this is a collaboration which cannot be represented, which cannot be factorized into 3 links, but is a pure, real filled triangle because it corresponds to a single paper written by 3 authors. Another kind of interaction you have in ecological species, this is a very famous nature communication paper of 4 years ago, in which you have interacting species. But you see, in this case, if you see my mouse, you have species 3, which interacts with the interaction between 1 and 2. So it's a sort of catalyst of the interaction between 1 and 2. And this cannot be factorized in 3 interacting with 1 plus 3 interacting with 2. So it's really something more, a group interaction. Okay, so as soon as you have this new representation, so you have now nodes and you have these hyperlinks, you need to define few things which are very useful. So when you have a network, usually, as Ron said, network corresponds to given adjacency matrix. So you use the adjacency matrix and you define the degree of the node I as the sum of a given of the ith row of such a matrix, which indeed represent the number of connections this node has with the rest of the network. When now you pass to this hyperlink, you have hyperlink of different dimensions, then of course you need to describe them with tensors. So you have to pass from matrices to tensors in general. For d-dimensional simplices or the uniform hypergraph, means hypergraph made only by the hyperlink of the same dimension d, of the same length d, you need a d-dimensional adjacency tensor. You can define a generalized degree of node I, which is how many of such d-uniform hypergraph are realized with node having node I or pass through node I. And you see this is a complicated sum over all indices of this adjacency tensor. But then you have another thing, which is the generalized degree of a link. So you can ask how many of such hypergraphs, how many of such hyperlinks contain the links ij, contain simultaneously, if you want, node I and j, which are connected in a network. And this is, as you see, another complicated sum of these things. And by means of this generalized degree of node and links, you can finally give a generalized definition of the Laplacian matrices. So you can introduce generalized Laplacians, which are made like this, are matrices now, again, matrices, whose elements ij are 0 if there is no link in the original network, if these 2 nodes are not connected at all. If there is a connection, then you put here the generalized degree of that connection, and as diagonal elements, you have, apart from d factorial, the generalized degree of node I. You immediately see that if you put d equal to 2, you have exactly the classical Laplacian. So if you have only links in your system, you have the classical Laplacian. If you have 3 links or 4 links, 4 hyperlinks, 5 hyperlinks, you have different Laplacian at different orders, d. Okay, so let me skip processes because I have no time, and let's go to synchronization. So now I want to describe synchronization in this very, very general thing. How can I do? I, again, like Guanrong did before, consider nodes as being dynamical systems. So I consider m-dimensional vectors xi, which describe the state of the node I. I have a function f from Rm to Rm, which describes the local dynamics, that is the dynamics of the system when it is unconnected. Maybe Lorentz, maybe Gressler, it may be whatever you want. And then I have a series of functions which describes these d+1 body interactions. So my equations are much more complicated than those considered by Guanrong, because you have derivative in time of this xi, you will have a local dynamics, then you have the usual pairwise interaction, the usual network interaction, which is described by this g xi xj. But then you have three-body interaction, you need this g2 xi xj1 xj2, and then you have four-body, five-body, up to the maximum number of the interaction that you have in your system. So this is a very, very big, huge equation, which we recently published in Nature Communication together with a group of Catania and with Mattia Frasca. And I want to report the basic idea, not exactly the details. You can go to the publication and read them there. So how you treat this system? So the first thing that you can show, and it's easy to show, is that as long as these coupling functions are all synchronization and invasive, that is, they are all zero, they all vanish in the synchronization manifold. So if you put together, you see, if you put here x66, it's the same arguments to the different variables, you get zero, then you can prove that the synchronization solution x1, x2 equal to x2 equal to x3 equal to xz exists. And moreover, it's an invariant solution. It means it is a solution which does not depend at all on the parameters, which in your case are sigma 1, sigma 2, sigma 3, sigma d, which are the different coupling strengths corresponding to different orders of interactions. Then you do exactly as what Ron did. I mean, you study how the deviation from this solution evolve, you linearize around, and now you can show the first part that all these terms, I mean, all these terms, all the terms of different G1, G2, this many body function, transforms into the corresponding generalized Laplacian. So you can again write a matricial equation in which you have here the classical Laplacian, here you have the Laplacian of order 2, here you have Laplacian of order 3, order 4, order 5, order d. And all these Laplacians are zero-row sum. So all these Laplacians have in common a single eigenvalue and a single eigenvector, which is exactly the synchronization manifold. So all these Laplacians, all the eigenvectors which diagonalize these Laplacians, they furnish an independent basis of the transverse space of such manifold. The problem is that these Laplacians do not commute in general. That means that each one is diagonalizable, but with a different basis, of eigenvectors. So what you do in general is you have to take one basis, one of such bases. For example, you take the classical basis of the classical Laplacian, like the one that is used in the classical master stability function, and you project the error into this basis, into the eigenvectors that are forming this basis. And what you get finally is a linearized equation in which the first component of the error, which is the one lying in the same direction of the manifold, is a closed equation. So derivative in time of xi1 depends only on xi1, whereas all the others are linearly coupled by means of this Lij2, Lij(d), which are nothing but the coefficients resulting from transforming the basis with diagonalizes the Laplacian of order d into the original, the classical Laplacian. So you took as a reference the eigenvector of the Laplacians. All the others generalized Laplacian have different bases which needs to be transformed by unitary transformation into this basis, and therefore you have all these coefficients. I hope that this is clear as a concept. Of course, this is plenty of algebra and cumbersome calculations, but you can go and read all of them into the preparation. So this is a linearized system from which you can extract a maximum Lyapunov exponent as a function of all the parameters that you have. And parameters are sigma 2, sigma 3, sigma 4, so you have very, very high dimensional parameter space. Now, in order to reduce this into some form of parametrizable equation, like you have in the classical mass stability, you have, of course, to make some hypotheses. So not always. This means you can treat this as a parametrizable equation, but there are relevant instances in which this stability condition, which is maximal Lyapunov exponent smaller than 0, can be seen as a function of a parameter. And these are the case, the trivial case in which your system is all-to-all connected. So you have all possible links, all possible triangles, all possible squares, all possible pentagons, and so on and so forth. Or when you have a structure and you have diffusive interactions, okay, with so-called natural coupling. That is, the interactions are diffusive. That is, you see, G2, which is function of three nodes variable, should be a given function h of xj, xk minus h of xi, xi. So it's a diffusive like in this sense. And natural coupling means that this function h2, h1, h2, x, and h of different order have to be such that when you calculate them in the synchronization manifold, they have to have the properties of h2xx equal h1x, h3xxx should be equal h2xx. And this means basically the fact that imagine a three-body interaction that node I is seeing j and k as a single node when j and k are interacting. Okay, so this is the idea. That's why it's called a natural coupling. Well, if you do this, it's easy to prove that you can merge, for example, with links and triangles, the two Laplacians, the classical Laplacian and the Laplacian of the triangle. So you can, at the end, obtain an exact parametric equation, and you can then obtain a master stability function with all the plots like the ones that Guanrong have shown to you. So, for example, these plots you have here corresponds to take Ressler system in each node. These plots corresponds to take the Lorentz system in each node. And you see you have bounded region of stability, unbounded region of stability, like this, for example, is an unbounded region of stability. It goes negative and then remains negative forever. You have situations which the system never synchronizes, so you never have a negative Lyapunov exponent. So this, and you see these are all possible interactions which are non-linear, of course, because otherwise you can factorize the same stuff. And you see you have interaction which take the x variable of the other two nodes and plug some nonlinear combination into the x variable of the first node. You take the y variable, the z variable, you make all the possible stuff. And you see here, there is, for example, in this case, what Guanrong called the union of periods. Here you have a region of stability, an interval of stability, then you have another interval of stability. So what Guanrong said, the union of intervals of stability. Here you indeed have as the Lorentz system. So you basically, what we did in this paper, we generalized the analysis of synchronization, the criteria, the necessary condition for synchronization, to a kind of interaction which includes all possible d-body interaction, and demonstrate that under some condition, that is diffusive-like interactions and natural coupling, you recover once again a master stability function approach with all the classes, with all the synchronizability, and all these things that was discussed largely by Guanrong. Second example, which I want to make to you, is when you consider now non-identical system, because of course, in the case of the master stability function, you have here the fundamental hypothesis that all the units are identical. That is, this function f, the local evolution, does not depend on node I. It does not contain the subindex I. Here, instead, I want to consider a model which is very famous, the Kuramoto model, in which you have group of nodes, each one is an oscillator, which with its own phase theta I, but each oscillator has a different frequency, omega I. So in absence of any interactions, these oscillators are non-identical, and therefore each one is rotating with their own frequency. So oscillators with different frequencies. In the classical Kuramoto, what you have here is a given coupling strength and the mean field, that is all-to-all coupling of the sinus of the difference of the phase. Now, this can be extended to three-body interaction, simply imagining here a double sum, of course, on J and K, because you need to. And the sinus of theta K plus theta J minus twice theta I. Now, notice that this is a sinus of, that is, sinus of A plus B is not A plus B. So you cannot factorize this into sinus of theta K minus theta J, theta I plus sinus of theta J minus theta I. So sinus of A plus B is not sinus A plus sinus B. So really here you have three-body interaction which are not factorizable. Then you can make another extension, because in two dimension, I mean, this usually you can see them as points which are rotating on the unit circle. So you can introduce in a plane a vector sigma I of coordinates cosinus theta I, sinus theta I. You can write the equation for such a vector, which are nothing but, here you have an antisymmetry matrices, and because the derivative of cosinus is sinus, but the derivative of sinus is minus cosinus, so you need an antisymmetry matrices here. And then you have the coupling term, which is with few trigonometrics, you can really write this way, which is the scalar product of rho, which is the order parameter, is the sum of all these vector on the vector sigma I, rho minus this times sigma I. So it's easy to see that you can do this. And when you do this, you also realize that there is no reason, really no reason, for stopping yourself at dimension 2. The only important thing is that this vector have to have norm 1. But you can imagine that you can go in 3 dimensions and considering points that are moving on the surface of a sphere, or in 4 dimensions, and you have points which are moving on the surface of an hypersphere, and so on and so forth. So you can make this extension to D dimension into simplices. So you see now you have the original Kuramoto model, in which you have introduced 3-body interaction, and you have extended this to all possible space dimensions. And here you see something really nice. First, there is a tremendous difference between odd dimension and even dimension. So in odd dimension, the transition to synchronization, you have the famous synchronization order parameter R as a function of lambda, the coupling strength, is more or less second order, or in presence of simplicial is first order. that is discontinuous. And instead, if you go in even dimension, you see that you have here a double transition. You have a first transition back. This is a backward transition from the synchronized state to a middle state, which remain stable for rather long time, and then it goes to zero, and you have a second discontinuous transition at zero, at lambda equal to zero, which is something very, very different, as you see, in terms from, and this is just changing the dimension of the supporting space. So having points in a plane is d equal to 2, having points in a sphere is d equal to 3, and they have a completely different stuff. Of course, we furnished here all the theory, because rotation theory of these oscillators, it's interesting to see in different dimensions. But much more importantly is this: even when you have d equal to 2, that is, you are in the classical Kuramoto situation, you can have, due to these three-body interactions, synchronization at negative values of the coupling. This is impossible to obtain for pairwise interaction. In the Kuramoto model, the necessary conditions in order to have synchronization is that at least a fraction, a non-negligible fraction of the population of oscillator must be positively coupled with the mean field. Instead, here you can couple all of the entire population negatively with negative lambda. Here you look, you have logarithm order 10 of minus lambda, and still you have a residual synchronization, which is a phenomenon which is completely dependent on these three-body interactions, and you cannot see in two-body interaction. That's why we submitted a paper that is called a contrarians. Contrarians means people that are coupled negatively to the mean field, synchronized beyond the limit of pairwise interaction. So this necessary condition for Kuramoto, we demonstrate, is not a problem of the Kuramoto model, it's just a problem of the fact that you consider only pairwise interactions. Okay, so this and many, many other things are collected in different stuff in which we now are interested very much on these higher order systems, because as I showed you, they have a completely much richer phenomenology, much richer emergent phenomena, and especially these states, dynamical states, which are completely new. I mean, not seen before. Here I list a little bit of publication if you want to have a read to the details of my my talk. And finally, I want to thank you and to invite you to submit your best papers to Chaos Autos and Fractals, which is the journal which I am involved as editor-in-chief, but as an editorial board contain a lot of famous names, including some who is here now, one of the organizers of the present conference, which is Mattia Frasca. Thank you a lot.
Thank you, Stefano. Thank you for this wonderful talk. So the floor is now open to questions, specifically for Stefano. I will say one or two, and then I will encourage the audience to ask a question to both our speakers. So there is, I think, one in the chat. So, Demi, do you want that we enable your micro so you can read your own question?
Yes, thank you.
Okay.
Thank you very much, Stefano. I was just wondering, in your view, what are the advantages of modeling these collective interactions that's like beyond pairwise interactions as hypergraphs instead of bipartite networks?
Well, bipartite network, you means you can actually imagine interaction, three-body interactions, like node with link. But 10 body interactions, I frankly speaking have no idea on how to put in a bipartite representation or a multipartite representation. I mean, if you have a 3-body interaction, you can say, okay, I have 3, I can see node I against JK, then, and so I can consider this a sort of bipartite interaction. I mean, here, a group of links, a group of nodes. If I have interaction involving more than 3 body, I don't see, but maybe in my limitation now, I don't have an idea now how to represent these collective interactions like as bipartite graphs.
Thank you. Okay, thank you, Stefano. So are there other questions from the chat? Or maybe here in this room, we have a bunch of people here following from the in-presence audience of the IFAC Chaos, but I don't see questions now. So let's start to see if we can do a small debate between Ron and Stefano. I will start with a question. So you both have talked about high order interaction, which is very, very nice. It's clear that the model you presented are different, but the principle is the same. So this is very interesting, and I think it's maybe also a future direction for new research in the topic. What I want to ask if there is a bridge between the 2 main topics you discussed. So what about optimality in a structure which has interaction which goes beyond the pairwise? It's a question that makes sense, and how, according to your idea, we can answer this question.
It's me first or Guanrong first?
You decide. You decide.
Okay. So I want, first of all, this gives me the opportunity of saying something about optimal synchronizability. I like very much the presentation of Professor Chen. The conclusion there, however, in my opinion, are limited to the case of symmetric matrices. Because for example, says the need of having cyclic, the more symmetry you have, the more. This is valid very much in the sense if you stay with symmetric interactions. It was proven from long ago that actually if you given any network, the real optimal synchronizability condition, that is L lambda 2 divided lambda n equal to 1, you cannot do better, is when you have an acyclic and unidirectional configuration. That is, if you take a graph, you can always define directions in each one of the links and weights on each one of the links such that you can always find a corresponding acyclic without cycles, therefore, and without and weighted configuration that guarantees that all the eigenvalues lambda 2 to lambda n are degenerate, and therefore lambda 2 divided lambda n is equal to 1. You cannot do better. Better than 1 is impossible. So this is really the maximally synchronizable graph. But as you have to pay that there is no cycle and it is not symmetric. So it's a sort of a tree embedded in a network. Mm-hmm. So this is really the maximal. And instead, if you want to remain symmetric, you have to use all the criteria that Guanrong just told you to construct the best thing you can do, which will never be equal to 1, but will approach as much as possible 1 as the eigenration. Here, I see immediately a problem, that up to now, this higher order interaction have been seen as purely symmetric. How you define a direction in a 3-body interaction, in a 4-body interaction? For example, in a link, it's normal. You have 2 nodes, so you have either I send to J, but does not receive from J, or the opposite. So this is the way a narrow. But if you have now a group interaction, can they have a direction? How can you define a direction? This is a serious problem, for example, that applied mathematicians are trying now to solve. Of course, you can have permutations between the members of this interaction. You can have partial direction, that is permutation with a sort of direction, associated direction to the permutation or to part of the permutation. And all these things, unfortunately, have not been solved yet. Actually, this higher order interaction really call for a big effort from the sides of applied mathematicians. They have to reformulate a lot of characteristics that are defining normal topology. For example, what is the role, what is the corresponding of centrality? You know, not centrality, ranking, which is the most important thing in networks. Eigenvector centrality in network, what is the corresponding? You know, these things, how can you define the importance of a node in this higher order? So imagine that you have in this representation, have in mind, you know, of nodes with different hyperlinks of different order, you may have simultaneous processes. And each process uses a given order. So you can have a node which is very central for a given process, but very not central for another process. How can you describe these things? So there are a lot of fundamental questions that have to be addressed by the level of the people doing structure on network, these applied mathematicians. And once these are approached, I think they will give link for answering your question, which is how can we obtain optimality condition based on these measurements? Because usually use measurements like spectrum, you are guided by optimizing these measures. So the issue is, in my opinion, that these higher order systems are really in its infancy and needs now a big effort from the sides of people coming from graph theory, really. Sorry, this is my opinion. Guanrong, you.
Okay. Thank you, Stefano, for the comment. That remind me actually that I did not mention. Now we are looking for those homogeneous and symmetrical structure that is sufficient only, but not necessary. So if you can find an example which give you the maximum ratio, but it's not symmetrical, this is not a surprise, and this is not a conflict. So we just can guarantee that if you have a symmetrical uniform case, you can guarantee that the ratio is very, very close to 1. But you can find, like you said, that you can find some cases where the network is not that symmetrical, but the ratio is still very, very big. Okay, so what I was talking about, from the whole process, you realize that we were only talking about sufficient cases, sufficient conditions. All right, so there's no conflict.
No, there's no conflict indeed.
Yeah, but thank you for brought up this so that I can make it clearer, even more clear. Your directional definition cases, I have no idea actually. So what I want to say about higher order cases is the following. Now, let's say you are talking about chromotal model. You look at the oscillator. You look at the phase. Let's say you have two oscillators, and then you can talk about the classical synchronization. So in the chromotal model, you have a theta 1 minus theta 2. You look at that. Now, if you have three oscillators on the circle, you can use a theta 1 minus theta 2 minus theta 3. But this is still in the lower level, not higher level topology. So we are talking about higher topology. It's not just a number of oscillators. We are talking about how they interact, how they are connected in the network structure. So you go beyond the ring, you go to a complex network, and then in the complex network, you have a triangle, you have a square, you have a heterohedron, you have that kind of structure, and then you can talk about higher order synchronization. Okay, if you still stay in the ring, it doesn't matter how many oscillators you have, it's still the first level of synchronization. All right, so you just put in the psi function, theta 1 minus theta 2 minus theta n, that still, you go back to the classical case with multi oscillators. So high order topology really is a good direction for young young researchers to look into, because the lower, now by comparison, we set the lower order case. We have been working on for so long, so many people working on that. We know quite well. So we just don't know that when the structure of the network becomes more complex, you see a lot of loops inside there. In higher level, we call it cavities. You have a lot of cavities inside there. You remember the heterohedron, right? And you go up more and more. And then that becomes quite complicated. Even the notation from Stefano's PowerPoint, you can see that even notations are quite troublesome. Very easy to make a mistake somewhere. So we don't know very much about the dynamics behind those higher order topology. In graph theory, in algebraic topology, people look into the structures only without dynamics. So the challenge for us is how to combine the dynamics into that really very complex higher order topologies. That's a challenge. So I'm interested in working on that kind of problem now with my friends, my postdocs, but we don't have much new result yet. So
thank you, Ron. Thank you, Stefano. Okay, so any other questions that maybe can be?
Or maybe opinion. We want to hear some opinions from the audience.
Oh, opinion, yeah, sure.
Right?
Sure.
What do you think?
Not necessary question.
Or maybe you have a better experience. Share with us.
Hi, Ron. Hi, Stefano. This is
Pietro. How are you?
Hi. Good, great.
Nice to meet you.
Very nice to meet you again. So thanks a lot for the talks. I don't have more experience than you, of course, but I have a question for you. So as Stefano said, the study of higher order interaction is at its infancy. So also from your replies to the previous questions, it's clear that there are many open questions and things to be addressed. So from your perspective, what would be the, if you have to name just one most pressing challenge in this area, what would you say, both from a theoretical applied perspective, whatever you think is the most pressing one?
Stefano, you have any idea?
Well, I think that really, you know, if you look at the story of how network theory has developed, there was Euler solving a problem, then 200 years of graph theory, which ended up with random networks. Then at the beginning of the new millennium, there was sufficient data and computer to look at the scaling properties of real networks from real world. And they discovered no network from real world is random. And you have, on the contrary, completely different scaling laws. Still you have universality classes. And this is the moment when physicists entered the game. Because, you know, we like universality classes, we like as statistical mechanics. And then you started, initially, the problem was really how you define a ranking. Because in network, you know, in graph theory, there's no ranking. Nodes are equivalent. If you think real life, what really made the change is the ranking. All important questions are ranking. Which is the most important gene for a given tumor? Google is making business in ranking web pages. What is, you know, why you are a physicist, you are paid so little, whereas Messi and the influencers in the web are paid so much, which in my opinion is a wrong way. We should be paid exactly as Messi, but that's another point. So, I mean, the issue of ranking is fundamental. It's really what marked the difference from classical graph theory into complex network theory. And in my opinion, the main problem there is, now, you have a ranking, and you know there is not a single definition of ranking. There are many. In my opinion, for example, the good question, asking what is the most important node in a network is a wrong question. The right question is, what is the most important node in a network with respect to a given process or dynamics? That is because you can have a network such that a given node is fundamental for a given process, but not fundamental for other. And this is extremely, I would say, more valid when you have higher order interactions. I make the example very little. Imagine that you want to model selling. You sell vacuum cleaner, like Checco Zalone in Quo Vadno, like, I don't remember, one movie of Checco Zalone. So you send a vacuum cleaner. So one way is you send a vacuum cleaner door to door. So this is pairwise interaction. But then you can imagine that you collect in a room 20 people and you ask, who is offering more for this vacuum cleaner? 1, 2, 3, 4, 5. I don't know how it's called in English. In Italian is una asta. So you make asta, okay? It's a different way of selling. In one case, it's pairwise interaction. The other is a multi-body interaction, okay? And now COVID-19 comes. And all the government have to put some limitations. So it says you cannot collect more than 5 people in a room. And now this means that the person, the salesman that was doing door to door is not affected. But the one who was doing asta is much affected because cannot collect more. So you see, this kind of stuff, I think they should be really reformulated. And of course, there is the intrinsic problem, which I think is from the side of mathematicians, that you are passing from matrix algebra into tensor algebra, which is a much richer stuff. And there you have to come out with new ideas of centrality, vulnerability, all these, I mean, things that actually we take for granted now for heterogeneous networks. So this, in my opinion, is the most important step now. And then you can use all the information for control. As you are engineering people, you like very much saying, we want to have more control on the system using, exploiting this multi-body interaction, or you can have optimization, whatever you want. I don't know if Guanrong agrees.
Yeah.
Okay, so Ron, do you want to add something or it's fine? Okay.
No, not at this point.
Okay.
Thanks a lot.
So any other questions or comments or opinion from the audience? Okay, so if not, I will go towards the end of this first talk. So let me share the screen just for a slide. Okay, I want just to remind the next talk. The next talk is 13 October. This time we will go to 4 p.m. Central Time, and it will be given by Eckhard Scholl and Florian Doffler. It will be about power grids under different views. So stop. So I want now to thank in a special way our speakers, Ron Chen and Stefano Boccaletti. You set up a very interesting discussion, and I think that as usual we learned a lot from your talks. And I also want to thank Arturo for the organization of the meeting and for hosting this joint session, and all the participants to be here in a virtual way. So now I want to go to give the floor to Arturo, which probably will say something.
Thank you very much, Mattia. I am very happy of this morning session, which ends our Chaos Conference 2021. I want just to say that organizing these conferences in an hybrid modality has been a sort of gamble that we wanted to pursue because we wanted to show that it's possible to stay again together, to try to share in presence, but also virtually, because the conditions are the conditions that we all know, and we have to face this novel situation, but without losing the good attitudes, the good habits. So I think that it was a necessary gamble to organize this conference in an hybrid modality, and I want to thank all the keynote speakers of this conference. I see that also Henk Niemeyer is connected to this session. I want to thank Rodolphe Sepulcre, which is not here because he had to go back to Cambridge. And I want to thank again Stefan and Ron for their today talks. Henk is here. I would like to ask him to give us a brief final comment from his side. Let me just allow him to. Okay. Now, Henk is alive. I give you the floor for some final considerations. Henk, can you hear us?
Yes, sorry. Yeah, thank you, Arturo. It always remains a difficult thing to you turn on your microphone at the right moment and switch off the camera, and I mean, I'm getting old probably in this, and I wish to. I made a opening lecture. I want to compliment you with organizing this meeting. With all the shortcomings, I can be very critical. It is difficult to have a hybrid conference. Honestly, I hate hybrid conferences so far. I've been involved now in a number of fully online conferences. I organized myself the European Control Conference with more than 600 people, fully online. But of course, we want to go back and meet each other, at least within the possibilities that exist. And that is what you did, and great compliment for that. And of course, when I gave my lecture, but also when I attended some of the other contributed lectures, it's difficult to have the full appreciation of what is happening on site. At the same time, it is what it is, and you managed at least to organize this quite nicely. So I compliment again. I mean, you should eat an extra very nice pizza at least. That is what you deserve. And I see also many others already giving a big hand, and that's what you absolutely deserve. I think it was interesting to see how you finally managed to set up the program for this chaos meeting. I think all in all, we may be happy to have seen this as a continuation. I think this is the fifth or version of the chaos meeting. Maturi, am I right?
It's the sixth. This one
The
is the
sixth,
sixth.
okay. But I think it has been a wonderful sort of continuation. So that's sort of what I wanted to say. Of course, I share with you to thank the other speakers, definitely also the contributed lecturers. I mean, Stefano and Ron, of course, deserve a big hand, but you already gave them. But I also want to compliment the people that attended and also contributed with their lectures. Thank you, and I think this is what I like to say. Thank you again.
Thank you very much, Henk. Thank you very much for your kind words. And let's say that we have another gamble in the future, next future, because we are planning to organize, hopefully in a fully in presence edition, the next NOLTA meeting in 2023. So it is organized together with the Japanese IEICE society. And we hope that in 2023 could be a fully in presence edition. So thank you once more again. Thank you, Mattia, for organizing this morning session. Thank you again to all the participants in presence here in Catania and virtual during these 3 days of works. Thank you again, and hope to see each other soon, hopefully in presence. Thank you very much.